Hello guys, welcome to the presentation of the paper entitled Analyzing Federated Learning Through an Adversarial Lens, published in ICML 2019. We are Ismat, Abderrahmen, and Houcem, and we're here to present this paper. So let's start with the motivation. In this age of information, data privacy is a major subject of contention. As you can see through the press publications in CNN and in Forbes, that this issue is very discussed. And also, a lot of tech companies can suffer from breaking their consumer privacies, such as the scandal that happened to Cambridge Analytica. So here, most tech companies live in a dilemma. Either they respect their users' privacy, or they use and abuse their data. Fortunately, at least for training the data, scientists from Google have created a new way to train the models while keeping the data on the user's devices. It is called Federated Learning, and it was published in a paper called Communication Efficient Learning of Deep Networks from Decentralized Data. So federated learning is about having a central model on a server that is sent to the clients that have the consumer's data on them. The model is then trained locally on the consumer's data, and then the gradient updates are sent back to the model and aggregated through a weighted aggregation method. Then the cycle continues. This model can be attacked as any machine model through two types of attacks, either data poisoning attacks or model poisoning attacks. Data poisoning attacks target the model's training data, causing the model's decision boundaries to change. They come in two flavors: clean label attacks and dirty label attacks. Clean label attacks inject perturbed training samples that are correctly labeled but cause the model to change its behavior, while dirty label attacks introduce new training samples that have a wrong label to a class. Model poisoning attacks, on the other hand, are when an adversary manipulates the training process to ensure that the model is poisoned in a targeted manner. Our attack falls under the umbrella of the model poisoning attacks. So, here, the agent attacks the model by poisoning his updates sent back to the server. To discuss the attack model, it is assumed that the adversary controls one non-colluding malicious agent, that the data is distributed among the agents in an IID fashion, and that the agent has access to a subset of the training data as well as to all the auxiliary data, drawn from the same distribution as the training and test data. For the agent's goals, they are to ensure the targeted misclassification of the training data, which amounts to maximizing the following equation. The agent must also satisfy some stealth metrics that are related to the accuracy and to these weight updates. For accuracy checking, if the update significantly lowers the model's performance on a validation test set compared to a model obtained by aggregating all the other updates, the server can flag the update as being anomalous. Therefore, the agent must satisfy the following equation. For weight update checking, if the distance between the malicious agent's weights and the benign agent's weights is higher than a server predetermined threshold KT, the model is flagged as anomalous. Therefore, the agent must also satisfy the following condition. So this paper has four main contributions that talk about targeted model poisoning, stealthy model poisoning, attacking Byzantine resilient aggregation, and also showing connections to data poisoning and interpretability. For targeted model poisoning, the paper uses explicit boosting to nullify the benign agent's updates and cause targeted misclassification. For stealthy model poisoning, it is used to avoid detection by the server, since the previous method can be detected with the use of stealth metrics. For attacking Byzantine resilient aggregation methods, the paper shows the efficiency of targeted model poisoning even with the use of these mechanisms. Finally, the paper shows the lack of effectiveness of dirty label attacks and interpreted decision making of the poisoned model. Now, I give the word to Ismat to continue with the approach.
Now I'm going to talk about the approach of this following paper. In this section, the authors assume that the malicious agent ignores the updates from other agents but accounts for scaling and aggregation. So our first approach is targeted model poisoning, and its strategy is boosting malicious update, no local training. For gradient-based optimizers such as SGD, explicit boosting is much more effective. For this, a malicious agent mimic the benign agent and run numbers of steps of a gradient-based optimizer starting from the global weight vector to obtain the malicious weight vector. Malicious agents try here to prevent learning model to learn to true level, or the adversarial goal is to misclassify the object. Learning model, it has to overcome the effect of scaling to do that. As the learning objective of a malicious agent is different from other agent, the malicious agent sent the final weight update by boosting it with a factor beta, implying that with the exact estimation the global weight vector will satisfy the malicious objective. The second approach is stealthy model poisoning, and its strategy is joint minimization of benign and malicious objective with distance constraints. A server can detect anomaly updates with accuracy on validation data and weight update strategies. So, to avoid a detect anomalous update, a malicious agent can improve validation accuracy or use weight update strategies. The adversary add training loss over the malicious agent's local data to improve accuracy of malicious model on validation data. As training data is IID with validation data, this will keep similarity of malicious agents update with benign agents update. Adversary does not have any access to current time steps generated by the agents. It updates the malicious loss function with respect to average update of loss function from other agents. The addition of training loss term is not sufficient to ensure malicious weight update because it is close to benign weight update, since there can be multiple local minima. So the adversary try to minimize the whole equation and try to calculate the minimum number of malicious the minimum value of malicious loss function. But there is a limitation of this approach, it does not ensure that the malicious agent's update is chosen in every iteration. So here's come the next approach, which is alternating minimization attack, and its strategy is decouples the targeted objective from the stealth objective. For this strategy, for each epoch, it first try to minimize the global weighted malicious weighted vector, give update to the malicious loss function. Then malicious loss function will boosted by the factor lambda, and it will add with the malicious weighted vector. And this final malicious weighted vector is the initial weighted vector for the next epoch. Finally, stealth objective for that epoch is minimized, providing the malicious weighted vector. The third approach is attacking Byzantine reagent aggregation, and its strategy is ensure convergence to models with poor classification performance. So it will follow two approaches. One is KRAM, and the second is coordinate-wise median. For KRAM, Byzantine robust aggregation rule based on similarity of the gradients or updates provided by all the agents at each iteration. They provide a theoretical analysis that guarantees robustness under certain assumption. KRAM choose the lowest value of loss factor to add with the weight vector. And the interesting fact about this approach is compared to the previous approaches, there's no need to scaling because the boosting factor is much smaller to ensure the model poisoning. Now, here is another approach is a coordinate-wise median. The coordinate-wise median approach is given a set of updates. In the aggregated update D or delta or loss function, the median is a one-dimensional median. The malicious objective is made with confidence close to 0.9. In this environment, there is convergence to an effective global model. Coordinate-wise median use information from all the agents while computing the new update. Thus, the method is fruitful. Now, I am going to pass this presentation to Abderrahmen.
To evaluate their approaches, authors have proposed the following experimental setup. They used the fashionista dataset to train a target model of CNN with dropout architecture. The model reached 91% accuracy. The dimension of the dataset was 60K samples for training and 10K samples for test. They also provided further results using the UCI adult census dataset to train a fully connected neural network that reached an accuracy of 84%. The total dimension of the dataset was 40K samples. The first dataset has 10 classes to label them, and the second is for binary classification. The adversarial goals for the first dataset is to misclassify a sample from the 5th class, which represents sandals, as a sample from the 7th class that represents sneakers. And the adversarial goal for the second dataset is to misclassify an individual that has an income lower than 50K as an individual that has an income greater than 50K. Let's start by representing the results of the first approach, which is targeted model poisoning for CNN on fashionista data using explicit boosting. This figure represents the results. The red line represents the malicious objective confidence of the misclassification on the global model, and the green line represents the validation accuracy of the global model. We notice that this approach succeeded to maintain the original validation accuracy of the global model, which is 91%, while reaching the malicious objective of the misclassifying one sample from class 5 as a sample from class 7, with a confidence of 90%. Authors also provided observations of the second stealth metric. So here they represented the comparison of weight update distributions for benign and malicious agent. Clearly here the update from malicious agent, which is represented in red here, is much sparser and has smaller range than the update from the benign agent. This result means that the malicious agent won't bypass the second stealth metric, and it is risked to be flagged as anomalous agent by the server. That's why authors proposed the second approach, which is stealthy model poisoning. Here's the results of this approach on CNN of fashionista dataset. So looking to the red line, we notice that using this approach, it's also a successive attack of targeted poisoning provided by the high malicious objective confidence. And the validation accuracy of the global model represented in green reached 91% in the 15th iteration. However, it is dramatically affected by the validation accuracy of the malicious agent in the 10th iteration. This means that the malicious agent update cannot be chosen in every iteration. And this is the limitation of this approach. In terms of the second stealth metric, as we can see in here, the comparison of weight update distributions for benign and malicious agent, the update from malicious agent presented in red is similar to the update from the benign agent, unlike the previous approach. which means that the attack can bypass the second stealth metric. Moving to the third approach, which is alternating minimization attack with distance constraints, here's the results for CNN on Fashionist dataset. So as usual, the red line represents the misclassification confidence. And clearly here the adversarial objective is achieved at the global model with high confidence starting from t equal to 3. And looking to the green line, we notice the convergence of the global model to a good performance starting from t equal to 2. And we also can deduce that the attack can bypass the first stealth metric because the validation accuracy of malicious objective is similar to the validation accuracy of the global model. And investigating in the second stealth metric, we can see that the update from malicious agent is still similar to the update from the benign agents. So the attack can bypass the second stealth metric too. Authors also used their approach to attack Byzantine resilient aggregation. For that purpose, they used two mechanisms of federated learning, the Chrome mechanism and the combed mechanism. So for the Chrome mechanism, the malicious agents update are chosen for 26 of 40 time states. Looking to that range and following the red line with the squares, we can notice that the attack of the malicious objective is achieved. And also looking to the green line here, we can notice the convergence of the global model to a good performance. For the combed mechanism, also we notice a successful attack with early convergence here if we follow the red line with axes, and also we notice a good performance of the global model shown in the green line with circles. Authors also provided a comparison between model poisoning and data poisoning for targeted model poisoning purposes. So to conduct their experiments, they use a dirty label attack as a data poisoning attack, which is adding multiple copies of the target sample to the training data with the appropriate target label. So the results were that the data poisoning approach was completely ineffective for this setting for this setting of learning, which is the federated learning model. And this was due to the fact that the malicious agent update was scaled comparing to the benign ones. Now, to set conclusions, there are 4 clear conclusions that can be extracted from the paper. The first one is that the first approach, which is the targeted model poisoning attack using explicit boost, is effective in federated learning model settings, but most likely not stealthy. The stealthy model poisoning can bypass the second stealth metric, unlike the first approach. And the third approach, which is the most effective one in terms of successful attack and stealth metrics, which is alternating minimization attack, can successfully bypass the 2 stealth metrics while maintaining a good performance of the global model. And finally, from the comparison part, we can deduce that the model poisoning attacks are much more effective than data poisoning in the federated learning setting. As the limitations of this paper, we noticed 3 probably main limitations. The first one is that the threat model assumptions for the adversary privileges are not always or could not always be applicable in practice, since sometimes an adversary could not have access to the training data. Also, we noticed that the paper sections are poorly structured and not well organized. And finally, authors did not set clear conclusions of their experiments. Thank you for your attention.